Morning, class. Professor Doney here for the next installment of Engineering 201. We are in the back half of Unit 3 now. We just finished up Chapter 6 on method of joints and method of sections. Now we're moving into Chapter 7. And the nice thing about Chapter 7, even though it's a little different topic, it actually continues with the method of sections way of analyzing these structures. So it won't be anything new necessarily math-wise, but just a little bit adjustment to the approach. So we're dealing with internal forces here in Chapter 7. Very important statement right up here. Got the work. Design of any structural member requires finding the forces acting within the member to make sure the material can resist the load. Well, that keeps going away there. And what we're talking about here is finding the forces acting within the member. So I'm going to highlight that. The forces inside the member are going to be known as the internal forces. So we want to know what's happening inside the structure, not on the structure. Everything up until now has been external loading, and then on the structure, on the beam, on the member, on the truss frame, whatever. So we're concerned about what's happening inside. Inside in this first one is the rebar or reinforced bars or steel bars that are inside the concrete. We want to know what's happening to them. Is there any shear forces or other forces going on? We need to know what's happening in these beams here that hold up this bridge. As you notice, they're thicker at the supports than in the middle. There's obviously a reason for that. In this billboard sign or this crane or hoist, maybe inside a car shop, we'll notice that they get thicker at the bottom, or they are thicker at the bottom than they are at the top. And we're concerned about the internal forces because to design any structural or mechanical member, we need to know what's happening inside the material so we know if it'll survive. And the way we're going to find those is method of sections, which is what we just did in the last lecture. Method of section. All right, so let's start with this member over here. We're going to be mainly dealing with beams. Beams are horizontal members, one-piece members that are used to support vertical loading. We're not worried about this being pushed left or right. We're worrying about vertical loading. And just like we did with method of sections, we're interested in a point or a section of the beam. All right, earlier we did sections of the trusses. We want to know certain members. Now we want to know a certain point. And this one, we're going to say we're looking at point B. B is going to be our point of interest. We're most concerned what's happening within the beam, within the structure of the beam, right below that 6 kilonewton load. Why? Because we see beneath loadings, that's where we see potential for changes, deflection, possibly deformation, and then possibly resulting failure. So the first thing we want to do is we're going to, before we pass a section through that, we want to find what's happening at the end. So we're going to do a free body diagram of the entire structure. Okay, free body diagram of the entire structure. And I'm just going to grab one of those from my notes so we don't have to suffer through me drawing that beam. And really all we did there is we added AX and DY. Now there should be a DX over here. The book doesn't add one here, even though it's a pin, right? A pin we would expect to have a X and a Y component versus a rocker over here, which is just a Y. And the reason they don't include that is because there's no horizontal force acting on that member. Now again, beams are meant to support vertical loading. So we're not concerned about horizontal where this thing is going to float away or slide away like a skateboard or something like that. It doesn't mean we put a roller or a rocker on both ends. It just means that we'll see that dx will equal 0. So let's do a quick solution of that, a free body entire thing, just to walk through the process. We're not going to completely solve this problem, but let's go through that. So if I sum forces in the x, set equal to 0, positive to the right, I'm going to get dx equals 0. And that's why they just didn't include it there. No need to include any further. All right, some forces in the y direction. See what's happening there, positive up. We'll have ay minus 6 plus dy equals 0. Can't really do anything with that, so we have to go to our last, which is sum moments. And I'm going to sum moments about D. I could sum them about A. It doesn't matter. But I want to find out, if I sum about D, I'll find out what's happening at A. And if I sum about A, I'll find out what's happening at D. So the A, let's see, AY will be minus AY times that distance of 9 plus 6 times that distance of 6, because it's trying to rotate it this way. This one's trying to rotate this way, which is negative. That's positive. The dy does nothing because it's going through the point of rotation, but we have to include that 9 there. That equals 0. That should tell us, therefore, that AY equals, what's that, 36 plus 9, 45 over 9. It gives me AY equals 5 kilonewtons. And I put that back up in here. And then for dy, it's at 6 equals 1 kilonewton. And by inspection, that should make sense because the ups, the 1 and the 5 up, have to equal the down, which is 6. And AY is supporting more because the 6 is closer to AY, and there's also a couple moment, the 9 over there, that is spinning counterclockwise. All right, so up to that point, nothing new. We found what's happening at the supports. Always a good thing to do. All right, the next thing we do, since we're following the method of sections solution model, is we're going to put a dashed line or put a cut or section right through the point of interest. Now, is the point of interest on the left side of 6 or just below 6 or to the right of 6? Okay. Now, many times the problem is going to tell you that point B is just to the left of 6 or just to the right of 6. I'm going to, just to make things easier, is I'm going to put it just to the left of the 6, just for this solution. So there's our cut. The book would probably call it AA. And they put our cut. And then we're going to have our two sections. We'll have our left section and we'll have our right section. I'm going to move the right section up here just because of room. and I'm going to redraw it up there. So this is just what's still on the right section. I'm going to have 1 kilonewton there. I'm going to have the 9 from the couple moment. The 6 is there, and then B sort of sits right there. That is our left section of the beam. Okay. Now again, since the whole thing was in static equilibrium, when we cut it up, the individual pieces are still in static equilibrium. Now I'm going to move the left section and put it down here, and I'm going to use what's in the book because they do a nice drawing of it. So let me grab that. There we go. Make that a lot bigger. All right, so here's the left section. And there we have that. And obviously it doesn't have the 6 kilonewtons because the 6 kilonewtons is on the right section. This is the left section. Now, if you remember when we cut members in half, the ones that are tension and compression, that there was internal loading that then became external loading. Okay, so when I make that cut at B, there's some loading internally that now becomes external loads that I have to include. And I'm going to draw those now. Just going to make this a little bigger so these come out nicer. All right. First, there's going to be a normal, and we call that N, and we can call that NB. That force component N is the normal to the beam. So I'll put over here NB is normal or perpendicular to the beam. I'm going to call it cut face. This typically ends up equaling 0, so I'll put that equals 0 question mark, because as you can see, there's no loading on the beam on this left section that is horizontal. Just like up here on the B, the right section, there's no loading horizontally. So that typically equals 0. All right, the next force component is V. And this is tangent to the cut face. And this is known as the shear force. Now the direction for the shear force, direction of the shear force is to cause clockwise rotation. That's what I say there. Choose clockwise. Is that what I'm supposed to say there? Choose, yeah. So what I mean is the shear is going to be this direction, but it's going to be pointing down because we're trying to cause clockwise rotation of this. So if you put a little pin in that middle, on the right face, it's going to be down. Now going back up here, since this force is down here, these internal forces on these two faces, right here and down here, have to be equal and opposite. So in this one, we're going to have the shear is up. Because it has to be opposite, equal and opposite of the one I drew down here in the left face. Also, that normal has to be opposite also. Let me put that in there. So there's the normal at B. There's the shear at B. So they have to be equal and opposite. So when I cut this, the left side will have this orientation, the right side will have this. Again, this causes clockwise rotation. The last one is called the bending moment. And that's where this is trying to bend, bend upwards or bend downwards as a beam. It sets up a moment there. And the moment is going to have this orientation. MB. And we want it to basically cause a smile in the beam for direction. Meaning if it's on the right side that I just drew on this left section, it'll be this way. If I go back up to here, it has to be opposite. So it's on the left face, it'll be that way. And this is very important. This is how we're going to set up all of them. I mean, we could use the right one up here too. But as far as on the face, that's how we're going to set up those three internal forces or loadings. Now that we've cut the beam, those internals now become external. Right? And these are the three that we're going to be working with. So the normal or axial force, the shear force, and then the bending moment. And again, these directions, just so we have them clear, for shear, depending on what face is the cut, the shear would be this way or this way because we want clockwise rotation. And for the moment, it's going to be this way or this way because we're looking for the smile. And that gives you guidance on the directions that you should have those forces. Okay. Now I'll just drop in here another drawing of that comes from the textbook. And I'll put it over here. That's essentially what we're doing at any cut. And then if we have them, we cut in half and we're looking at both sections, it would be this here. All right. So this side obviously corresponds to that side for the left. This is over here, the right. But what it's showing, it's awful. It's showing that they'll be sort of corresponding. So the normal and normal, right? The shear and the shear. And then if I can find another color here, bending moment, bending moment. I'll take that off because that actually covers up. I don't know if this allows me. Yeah, it's green. I want to use a different color. Bending moment, bending moment. There we go. And that really is the whole part here on internal forces. We're going to make a free body diagram, find support reactions, make a cut at the appropriate point of interest. And depending on which face we use, we just then some forces, some moments. Now the question may come out, okay, well, which one do we use? Do I use the left Twix or the right Twix, as they say? I use the left section or the right section? Well, at that point, it's typically easier to use the left section because everything is measured from positive goes from left to right. Another reason to use the left section, if there's more things going on, if there's more loading on the right side, then I would pick the left side just because it'll be easier math-wise. The other point is as I said, with the distance, it starts x equals 0 at A and goes to 3 at B, and from B to D it goes 3 to 6. We'd have to be careful distances when we're doing moments here, just because the distance actually starts over here at A. All right, what I'm going to do is just finish this problem real quick here. So let me grab this section again. Let's see if I can just copy it. And let me go to the next page and finish that problem. Let me see if I can do that. This is a pretty easy one. All right, so we're going to have, let's see, coming out of here, we have the normal. So it's a normal at B. We're going to have the shear. Again, that's going to be downwards because we want to go there. And then we have the moment because it's a smile. So this is the left section. And we know we found out that moment. All right, so how do we solve this? We did the free body diagram, one. We did FBD. Come on. We did the free body diagram. We found the support reactions. That was AY and DY. We made the cut. And we labeled the normal, shear, and bending moment. And now we just apply the equations of equilibrium. And hopefully by now you know those are some forces, some moments equal to 0. Right? The two keys to get the final exam that don't know what to do, some forces, some moments. All right, we're summing it on this left section only. So let's sum forces in the x direction equal to 0, positive to the right. We're going to get MB equals 0. Again, that is typical. Okay, sum forces in the y direction. Positive up. Plus 5 there at A, minus VB equals 0. Therefore, the shear at B, guess what, equals 5 kilonewtons. Now, again, since this is the left section where we cut it at B, if you look at the right section, it'll be, if we solved it, it would be 5 kilonewtons upwards. Because this down on this side, the 5 down this side has to equal and be opposite or cancel with the 5 up on the other section. All right, some moments equal to 0. Here's the important step that I didn't include yet. When we sum moments of a section, it's going to be about the cut. So we're going to sum moments about point B. Okay, we sum moments about B. Why do we do that? That means the normal doesn't cause a moment and the shear force doesn't cause a moment. Now, I could sum moments about A and then use the shear to create a moment, but if I make a mistake in summing forces in the Y, that carries over to summing moments, doesn't help me out. So we always take the moment, sum the moment about the cut. So summing the moment about the cut is going to give us minus 5 times 3. That's from this over here, plus the moment at B. That accounts for everybody, equals 0. Therefore, the moment at B equals 15 kilonewton meters. And that's our solution. Now we know exactly what's happening at point B. We can design this beam member or the structure to make sure it can withstand 5 kilonewtons of shear. and 15 kilonewton meters of moment or bending moment internally. And that's really as simple as it is. If I go back to the previous page, if we want to know what's happening at a different point over here, like, I don't know, C, I would just cut at C. If I want to know a D, I cut at D. I already know what's happening at D because it's a support reaction. But I just need to find out my cut of interest. So our steps again are to free body, find the support reactions, cut and label, and apply the equations. That's really our process for solving them. Now, just so we're aware that this is in 2 dimensions, that this could be done in 3 dimensions. We're not going to do one of those problems right now, but we could. We have the cut face. Again, here's the normal that we just worked with. But since it now has a 3rd dimension, we'd have to worry about things going up in the Z and also things coming out here in the X. But it's the same thing. Shear, normal, bending moment. And those all act at the geometric center. These bending moments are more, the moments like in Y are sort of torsional. The one in this one becomes torsional, meaning it's sort of twisting. The moment Y is more of a torsional one, like twisting of a bar. These others are just normal bending moments. And they all act the geometric center or centroid of that. All right, so let's go through just a handful of problems. We're going to start out really easy. And let me just pull an old drawing over here. And this one we can almost do by inspection. And I think I've said that before. By inspection means looking at it and coming up with the answer without having to do any math at all. Okay, so let's do that. And this one, as you look, we're going to have looking at points. Oh, it went away. We're going to be looking at points A, B, and C. I'll highlight there, A, B, and C. And this isn't really a beam, it's just have vertical supports only, so it makes sense when we make a cut there, there's not going to be any shear. There's no left and right against the surface, the cut surface, and there's no bending moment because we have symmetry. So let's go through these nice and quick. If we look at point A, that means we're going to make a cut at A. And what do we have happening force-wise? We have 550? 550 down, and we're going to have the normal. Now, I could draw the normal as up or down here. I'm pretty sure if there's a 500 down, there has to be a normal up to support that. I've cut it right here so there's no other forces acting on it. So I can just say by inspection, that should be 550 straight back up. Hopefully you can see that. Let's look at B. It's going to have that, comes down. There's another circle, comes down. It's cut. Here's B. The loading we have is still 550 on top. There's 150 up, 150 up. Here would be the normal. We can see that that normal should be in the other direction. And really just by summing forces in the y direction, we could get this. But NB has to equal all those, so we would have minus 550 plus 150 plus 150 minus MB equals 0. MB is going to equal minus 250, which means it's the opposite direction. That means it'll equal 250 pounds up. And pretty straightforward there. And we should be able to see the same thing if we do C. Now we have 700 the other way. And if you go through that, I'll let you go through that. At C should equal 950 pounds up. Very simple, but here's the point of this problem that I want to show you. We go all the way through here. We do A, we go B, then we come to C, and there's all this happening up top here. All these forces acting. It starts making it a little more complicated mathematically. Question comes up, couldn't we start down here and just use this bottom section? So if I section here at C, that'll have the force of Y, or the force at the bottom. Could we find out what's happening here? Because that would be the normal at C. Well, we would need to know what that force is at the bottom, and that's really just the normal force from the ground. So that's sort of F of N of the ground. We would need to know that by summing forces in the Y equal to 0 on the entire structure. And if we did that, we have minus 550 plus 300, so that's minus 250. Minus another 700, it's minus 950. This would come out to be, on the bottom here, this would come out to be 950 up. And if that's 950 up, we would end up being 950 here down, which is essentially what we got just on the upper cut here. So these numbers would correspond, and that would make sense. All right, question on that one. Should be straightforward, I think. All right, let's go to the next one. Example. And let's pull a beam out here. A little more complicated. There we go. All right, we're given the loading on the beam. We want to find the internal forces at point C. Internal forces at point C. That's our interest, so I'll just highlight that right there. All right, so what's our plan? Well, our plan is to follow what we've been doing. We're doing the method of sections. And our method of sections should include 1, doing the free body, 2, find support reactions, 3, cut and label, And then for some forces, some moments. All right, so that's our procedure moving forward. So what do we have? Support reactions. Right here, we're going to have, that doesn't come out really good. Different color. There we go. AY, it's a roller, so there's no AX. We're going to have a BY there. We could put the BX in there, but as I said, because there's no horizontal forces here, we don't expect that anything's going to happen. All right, within this free body diagram, before we find the support reactions, we have to deal with this distributed loading here, right? And if you remember how we deal with that, the resultant force is going to equal, the resultant force equals, so I'll just go FR, the area under that curve, which is going to be 3 kip feet times 6, which is going to be 18 kip. And if you remember, a kip is 1,000 pounds. And we have it acting right there, basically halfway. So I'll put half and half. That's for the free body part. All right, so let's find the support reactions. We did a free body. Let's do support reactions. So this is step 2. We kind of did one right here. Sum forces in the X equal to 0. I'm going to have Bx equals 0. That's the nice one. Okay, sum forces Y direction, positive up. AY minus 18 plus BY equals 0. Can't do anything with it, so let's sum moments. Positive counterclockwise. And we can find the moments at B, or we can find the moment about A. Really doesn't matter. Let's just choose B here for the sake of solving it. I'm going to have 18 times 912 minus AY times 9 equals 0. That tells me that AY is going to equal 18 times divided by 9. I get 24. And if I put that back up here, then BY is going to equal BY, let's see, 24. Okay, 24. Six. But it actually ends up being 6 down because that ends up being a negative right there. Right, ends up being a negative 6. So I translate that to, instead of being up, it's now going to be down. And that kind of makes sense because if this big 18 is pushing down about that roller at A, it's probably going to cause this to tip up, this right section to tip up. So we would change the direction of that to be down. And we'd have to remember that. All right, at this point, we're going to section. We're going to section at C. Now, looking at the two sections, to the left of that orange line at C and to the right of that orange line, the left cut versus the right cut. I hope you would agree the right cut has a lot less going on. The right cut only has the reaction BY. The left cut has the distributed load. It has the reaction at A. So in this case, using the right section, I think would be preferable. So let me come down here and redraw that right section. I have 6 down. On the face cut, I'm going to have the normal, which doesn't matter because there's nothing going on. I'm going to have the shear. The shear is going to go up. Because we want it to spin clockwise. And the moment here. And at this point, we just, again, sum forces, sum moments. So I sum forces in the x equal to 0, positive to the right. I get the normal at C equals 0. Positive up, summing forces in the y equal to 0. Shear up, minus 6 down equals 0, means shear equals 6. What are we? Kips. And it's up direction. Again, it doesn't matter because on the other side the cut is down. And then we sum moments about the cut. That equals 0. We basically have minus the moment because it's in the, I went the opposite, wrong direction there. Hang on, let me wipe that out. Positive counterclockwise, that gives us negative moment. Minus the 6 over here acting, I think that's 4.5 feet. Yep, 4.5. That is a good 0. It tells me the moment is going to be a negative 27, which just means that it's 27 on this face, this direction. And that's kip feet. And that solves the problem. Now, again, we could have done using the left section. It would just involve a little more math because there's more forces acting. Okay, questions on that one? Just drop something in the chat. All right, appreciate that. All right, I have one, maybe 2 more problems for us to go through, so this is certainly a shorter lecture. Let me label this one again, EX. And I'll call that beam 1. And beam 2, and let me pull that over here. All right. Looks way more complicated, doesn't it? Well, it doesn't matter how it looks. Let's just apply our process that we use. Okay, the process that we use to solve this. So given the loading on the beam, we want to find the internal forces at point B, or point F. Sorry, let me highlight that. There's F. And our plan, follow the procedure. Follow procedure. All right, so our procedure is, let me put it way over here. Free body diagram, supports, cut and label, some force, some moments. Hasn't changed. Doesn't matter what the object or the structure looks like. Supports. Now this has a pulley in it, so we're like, well, we've never dealt with pulleys. Well, we kind of have. We don't care what's happening outside of the structure. The only thing that C tells us is there's a pulley there, and it tells us that this is one continuous cable. What that tells us is the force coming up here at B for that tension at B is going to equal the tension at D. Excuse me. That's really all it's telling us. So we would refer to them as tension and tension. That's the only thing that matters for us from that pulley. And then from there, I can put an AY over here, and I can put an AX. Now, since there is a component in the X direction of the cable at D, we now will have some force set up in A. We can expect some force set up in A. All right, so what do we do? Did a free body. Let's find supports. Some forces in the X direction equal to 0, positive to the right. AX plus tension cosine of 45 to the right equals 0. Really doesn't help us. Some forces in the Y equal to 0, positive up. AY plus tension sine of 45 plus tension equals 0. Still not helping us, so we have to sum moments. We can sum moments about A. See if that'll drop out the most. We'll have, oh, we forgot the moments of this thing. Sorry, totally forgot. I'm looking at all this complication down here and totally forgot to add that. That'll be in the Y direction. So that'll be centered there. That's going to be the force resultant, and that is equal to 300 times 6. So that should be 1,800 down. So this one should have, let me clear this out, minus 1,800 equals 0. That looks better. And the moment about A, let's see, will be the tension on the end times 6 plus the tension sine of 45 acting at 3 minus 1,800 acting at 3. That has to equal 0. Tension here will be 5,400. 665 newtons. And I can put that back in here, and I can find out what AY equals, and I can put that in here and find out what AX equals. And that's 665 times 1.707 minus 1,800. I think that comes out to be 665 again. And then 665 times 45 would have to be about 470. All right, so we did step 2. We found the supports and solving it. A little more complicated just because I forgot that there, but still nothing out of what we've already done. Moving on, we're now to the cut and label. We plan to cut this right here at F. And we will have a left side and a right side section. Now, in this one again, I think you'll agree that the right side section is way cleaner, meaning there's a lot less going on. Than the left side. Okay. Now we just have to be careful. Let's draw this section here on the right side. We're going to have forces 665 from the cable. We're cutting at point F. So there's the normal. Here's the shear. There's the moment at C. Now, the only thing we're missing here is we have to account for this portion of that distributed load, right? For this portion of the distributed load. Now, the whole thing is 1,800. That means half of it over here would be 900. Same here. And then half of that would make this 450 in here. And we put that as the center, so we're going to have 450 acting downwards. Very okay with that. We have to include that distributed loading. We found the result originally just to help find reactions, but once we go back to the cut, we have to include that there. That is the 450 that I have written right there. So that's a free body of that section. We could go in here and put some dimensions. That becomes 1.5. That's 0.75. There's 0.75. So they're just cutting and labeling. So we're going to use the right section there. Let's go ahead. Sum forces in the x direction equal to 0. It tells us that the normal at F equals 0. Sum forces y equal to 0. We have, let's see, the shear up minus 450 plus 665 up equals 0. The shear is going to equal 10, 11. What do I have here? Shear up minus 450. Oh, that should be a plus 650. Sorry. That should come out to be 215 with units. 215 with units. Just fix that. And then we're going to sum moments again about the cut. That equals 0. That means we have minus m, the moment at F, right? Minus 450 times the distance of 0.75 plus 665 times its distance, which is 1.5. That should all equal 0. And if I go through that, MF is 660 Newton meters at the cut. Okay, questions on that problem? All right, where do we go next? Well, we just found, let's say if we have a beam here, let me just draw a beam. Actually, let me pull back one of the earlier beams so I don't have to try to draw some messy. All right, this is the one we did at the beginning, right? In the beginning, we did this problem and we found out what's happening at B. I could also ask you what's happening at C or F or K, because we want to find the point that has the maximum bending moment or the maximum shear, because if we find out where the maximum is, if we know where the max in that beam occurs, we can just make the design limits or the design conditions to use that or those maximum or maximi, either way, to use the max in each case. Now, we typically think of it where there'll be the most deflection, and sometimes it's below a point load or some distributed loading on top. But to really find it, we'd want to check all points on the beam. We want to check every point along the beam there to make sure we didn't miss the maximum somewhere. But as you can see, that would be a lot of work. That would be, if we want to check 50 points, that's be 50 solutions, 50 cuts, 50 solutions. Becomes a little old. However, if we can learn to, and this is what we're going to do in the next lecture, if we come through and create shear and bending moment diagrams. All right, I see a question up there. No? Somebody raised their hand? All right, not sure if anybody can hear me. Saying there's some connectivity issues. Just give me a second. Okay, can somebody just drop in the text if they're still hearing me or seeing this? Okay, thank you. I'm just seeing some red X's on some things. So I'm not sure what the issue is, but okay. I'll give it a second then before I continue. All right, so continuing on, where do we go next? We want to find the max. That would mean checking all the points in the beam. That would be a lot of work. But if we can come up with shear and bending moment diagrams, meaning we can find what's happening, if we can find out what's happening across here, and I'm just drawing these representative, it's not the exact ones. And we can come up with these diagrams or plots. We can visually see immediately where the maximum occurs. And here it just happens to be at B where we look. And to create these bending moment diagrams and shear diagrams or plots that I've drawn below there, it's not any more difficult, because what we're going to do is we're going to create sections that start from the left end, the right end, and anywhere there's a loading. So we're going to create two sections, and we're going to solve these doing the left section and here the right section. And we're going to be able to generate a function that tells us those lines and constants and plots. And we're going to find a way to solve so we can do diagrams. And that's what we're going to do next week. Okay. So next week we're going to do shear bending diagrams. I'm going to show you some shortcuts. And 3, we have to talk about cables briefly. Now the cables I may do offline and post that video just to keep us on pace again. I want to give enough time to the diagrams next week and the shortcuts, so I may post the cable one as an offline recording and post it. Okay. So at that point, so where go next? And then this one will be asking any questions with what we did today. And I'll take a look in the chat or see if anybody jumps in with anything. And otherwise, we'll be done for today. Thanks, Jaden. Appreciate that. Anybody else? You can just leave, or you can say all's good or ask a question. I'll hang out for a second while people leave. All right, sounds good. Maximum implies that there's only one to be a maximum. There may be others that are close, but we would start, again, we're trying to find all the loading in the beam so that the designers can select the appropriate dimensions of the beam. So if we find the max, we report that, and then they would go from there. No worries. All right, everybody, enjoy the day. Hopefully, if you're on the East Coast, I think the rain is stopped for the day, and we'll have another nice day today and tomorrow. So have a great one. See you guys and girls later.